Okay, so this next section we're working through is section 3.4 about undetermined coefficients. And this is, again, a pretty straightforward section where there's only a few things for us to do. We're just going to talk about the general approach to solving this type of problem. We're going to talk about one quirk of the method related to picking what we'll call G sub I. Um, that'll make sense when we get to that point. And then we're just going to work through a lot of examples that kind of demonstrate that main idea. But before we do all that, let's kind of talk about the method itself and why we're covering it. So what we're going to do is we're going to use, not determined, this method called undetermined coefficients in a very particular situation. And it's going to be when we want to find the particular solution that will denote y sub p to a constant coefficient non-homogeneous, barely fit that on the slide, differential equation. And since there's a little bit of vocab in that blurb right there, we're just going to write down what we mean. When we say constant coefficient, that's the type of differential equation we learned to work with in the last section for some constant a sub n minus 1, so on and so forth, all multiplied by y and its derivatives. That's a constant coefficient differential equation. And last section, we learned how to set it equal to 0 and solve that. And actually, when we would do that, we would kind of find the fundamental solution set. Y1 through Yn of the form, actually, we'll just do Y1 e to the m1x, Y2 equal to e to the m2x, so on and so forth, down to Yn. Maybe those would be like sines and cosines if you had imaginary roots, but you get the idea. You learned how to do that last section. That's what constant coefficient means. The important part here is the non-homogeneous part, which means that there's some g of x on the right-hand side, a function of x. And whenever we have non-homogeneous parts, then we sort of take our constant coefficient method and then put it together with this other method that helps us find some y sub p, a particular solution, using undetermined coefficients. And kind of once we have those two different pieces together, we can find the general solution to the ODE using superposition. That's just going to be y equal to c1 y1 plus c2 y2 down through cn yn. That's how we find a general solution to the homogeneous problem. And all we have to do is add on that y sub p that we find using undetermined coefficients. So that's why we learned this method, for this little last piece that we need to find solutions to these more complicated differential equations than we worked with last week. And the steps we're going to follow are going to be pretty straightforward, except for one little quirk that we'll discuss in more detail next. But all we're going to do is we're going to assume that we know what y sub p sort of looks like. So we're going to say it looks like some a times g1 of x plus some b times g2 of x, so on and so forth, where a and b and any letters you want to put after that are undetermined coefficients. So they're just constant numbers that we don't know what they are yet. And they're where the name for this method comes from. And the g1 of x, g2 of x, so on and so forth, are sort of related to the right-hand side of our differential equation, g of x. So whatever this extra bit is right here that wasn't part of the regular constant coefficient problem, that somehow determines what g1, g2, so on and so forth are, and we'll discuss that next. But assuming that you do know how to build that y sub p, we just want to make sure it's a solution of the differential equation. So same as always, we're going to just plug it in and see what happens. And always that's going to involve like taking derivatives. So that you can actually fit it in. After we do that, there's just going to be a little bit of algebraic manipulation where we're going to do something that I call group-like terms, which means that they just sort of look like the pieces G1, G2, so on and so forth, and then set groups of coefficients equal to each other. And that sounds a little bit vague right now. It'll make more sense when we do examples. And I'm going to put a little star there. We'll come back and kind of talk about how that part works after you've seen an example. But then after you do that, what's going to happen is you'll just sort of reduce your differential equation to a system of algebraic equations that you have to solve. And then after you do that, you'll sort of find numbers for what A, B, so on and so forth are. And then you just have to plug everything back in so that you have your yp equal to A G1 plus B G2, so on and so forth. So the way it's going to work is that you'll just sort of assume the yp has a shape depending on these G1, G2, and then find the constants that make that true. And then once you know those constants, you know what yp is, and you've finished your task, basically. So the tricky part here that I kind of glossed over is that you have to learn how to figure out what G1, G2, so on and so forth are. So what I'm going to do is I'm going to just tell you that there are going to be like 3 guiding principles for us. And I'm going to tell you the first one right now, and then as we work through examples, you'll see the other ones come up. So our first one is just going to be that we use terms that appear in g of x. So for example, if we had y double prime minus y prime minus 1 equal to 2x squared plus 3x plus 4, this is our g of x. And so I just want to pick all the terms that show up in g of x. So I would say, okay, g1 is x squared, g2 is x, g3 is 1. That has all the functions of x that belong on the right-hand side of that equation. And you'll see that in the example that we do next. And then there's going to be sort of 2 more ideas. That should give me enough room to write. So you might want to leave this much room in your notes, but I think that they make more sense when we do examples. So in the next video, we'll start an example that shows that premise A, and then we'll come back, write premise B, do an example that shows that, and so on. So just click on through whenever you're ready for that first example.